Hello, good afternoon to everybody. We just go through some documents here before we continue on our lecture on some updates that I did in our course material that's available in this course website here. So because it takes a while to Zoom to process the recording and then for me to edit the audio and upload to YouTube, people that cannot attend the class live would have to watch it later on, would not be able to take the quiz up to 8 p.m. today. So I pretty much made it like a wider window when you can take the quiz. So it's from 4:30 from the day of the class until noon of the following day. I suggest you, so this is on the top of page 3 of the syllabus. And this link here is the one with instructions about the quiz and exam. I suggest you reading this document before you start the quiz. Pretty much, we're gonna have 2 multiple choice questions for this first quiz, for quiz 1. It's gonna be available today from 4:30 p.m. until tomorrow at noon. But once you start the quiz, you have only 5 minutes to complete it. And you're gonna see the correct answers only tomorrow at 1 p.m. So only tomorrow at 1 p.m. after the quiz has closed, you'll be able to see the correct answers to the questions. It's pretty much a bunch of multiple choice questions that I created about chapter 1 and about these topics that we have been discussing in class. And Canvas will select randomly 2 questions for each student, so your questions will be all different. And like I said, of course, this is open book. You can see your notes, you can see the slides. So just be prepared because there is a time limit. And I even have the suggestions here. Remember, that's pretty much only 2 minutes and 30 seconds per question. All right. And in Canvas, the way that you're going to see there, so this is the view that you have to the Canvas website. And if you click here on assignment or on this picture here, assignments, you go to the same place. That's where the quiz appears. It's not available now. It says when it's going to be open and closed, but that's how you're going to do it. And I just suggest, again, you reading that document that explains the structure of quizzes and exams. So that's where you're going to do it. And then your grades are automatically posted, but you're going to be able to check the correct answers just at 1 p.m. Okay? Any questions about that? In the lecture 1, I added some slides to the PowerPoint. So if you had downloaded, you just download it again in the website. It's just that first lecture related to chapter 1. I updated again, adding some more things. And the major changes is adding this topic here, ratios, rates, and probabilities, that they were kind of like separated lectures throughout the semester. I just decided to organize them all here. And I just rearranged here where the topic about COVID-19 is. I put it right after we discuss what variables, observations, and databases are. One student in the previous class, she asked a good question about like, what is this problem here of data reporting anomaly results towards the end of July for Texas. And then I suggested going to this link here and then clicking on this link. So just to show you what it is about, that link is this one here. So at the top of the page, you're gonna see data about Texas. And then you just go down. These are the 2 figures that I collected, one about cases and the other one about deaths due to coronavirus in Texas. And if you just click on this link here, it just goes to this page, and then it mentions that in July 16, the state reported 1476 backlog cases from prison inmates in Anderson and Brazoria counties. but the major changes are here. Texas changed its methodology for reporting coronavirus deaths to use death certificates, causing a spike in the total number by including deaths that were not previously announced. And an important thing to highlight is that these confirmed cases and deaths are widely considered to be undercount of the true toll because exactly not enough tests and so on. So someone else in the class asked the question, oh, maybe we are overestimating these cases and deaths because we are confounding them with flu. So it's exactly the opposite what public health experts are saying. If you click on this link here about, if you want to know more details about the changes in the methodology, it's going to take you to this page. And here you're going to see that the Texas Department of State Health Services improving the report of fatalities due to COVID-19 by identifying them through the cause of death listed on death certificate. These methods allows fatalities to be counted faster with more comprehensive demographic data. So actually that increase is just saying that now we are counted better the pandemic in Texas. As of Monday, back in July, death certificate data has identified 5,700 fatalities among Texas residents, including 44 newly reported today. That compares with 5,038 deaths reported under the previous method. So the previous method was actually undercounting the deaths. And the new methods that's more accurate is counting the deaths more in a better way. So I really like that question from in the last class because it makes us go deeper to understand the methodology. So here I first went into the New York Times website itself, found our notes, and then they provided this link that we can get information straight from the state of Texas, right? From the Texas Department of State and Health Services. We have to know the COVID statistic for tests or quizzes? No. Usually, I know that some professors, they ask exactly numbers. I don't. I usually try to ask you to understand the logic behind it. How exactly what's the interpretation of specific rates? What's the interpretation of specific ratios? If one rate is increasing, what does it mean? So for example, in that previous lecture, when I discussed the ratio between testing cases, my idea is that you should not remember exactly these numbers, but understand what does it mean. When this ratio increases, it means that tests proportionally are increasing more than cases. If this ratio decreases, it means that cases are increasing proportionally more than tests. So that's the idea. This data that I got from our world in data compared countries, you can just go to this website here and then you can play a little bit with the data. Like here, for example, I'm just comparing Italy and the US, just using linear, which is more like easier to understand it, confirmed cases per million people. So this is the rate of cases of COVID-19. Rate, because the denominator of this indicator is the population of the US and Italy. And you see the pandemic, as we know, started earlier in Italy, and the US reached the number of cases a few weeks later, similar the rate of cases as Italy some weeks later. And then Italy started to decline a lot. The US started to decline, but then relaxed the measures and then went up again, and it's now declining again. And again, these are rates taking into account the size of population in the US and Italy. And this is the graph for deaths. So you can select countries here, you can type the number of the country here, and then it's gonna appear on the screen on the left. And here showing that the rates in Italy were higher in the past, but now in the US, the death rates are higher than in Italy. So it's just like some data, public available data that you can investigate, and this has been updated really frequently. So pass through this, everything, the quiz, and so I will start now. We talked in the previous class about demographic models, the difference between social demography and formal demography, and then we kind of stop here talking about cohorts and generations. I mentioned that cohorts are a group of people that experienced a common event during a given time period. Usually, we use cohort as pretty much trying to capture people that were born at the same time, but the correct way to classify that specific kind of cohort, those are birth cohorts, when these people are born around the same time. And those birth cohorts are also usually referred as generations. And the idea is that if you understand these opportunities and challenges that these specific groups face throughout their lives, you can have a better idea of how the generations will be in the future. And I showed here some examples of cohorts, and I mentioned that the millennials and Generation Z, like this time period here, there is not a consensus among social scientists of what these cohorts are, but it's just to give an idea. That's one way to analyze groups that were born around the same time. But I also said that these time intervals are kind of wide. If you want to go deeper and understand the specificities of people born around the same years, you would have to cut it down into shorter time intervals. The lucky few cohort, they were born between 1929 and 1945. That's the cohort that was born right after the Great Depression of the 1930s. And exactly because of all these economic challenges that people were facing, so people start to have fewer children, more issues of finding jobs, so fertility decline. So they were fewer compared to the much larger number of persons in the following cohort. And the baby boomer cohort is the following cohort that was born after World War II, from 1946 to 1964. And then at that time, the Western countries, they were growing much more, in the US specifically, and that created a lot of like life opportunities, job opportunities, and better quality of life for more people, and then people start to have more children. And the smaller size of the lucky few has enabled them to experience higher employment rates and greater variety of social opportunities than members in the preceding or following cohorts. The baby boom cohort is really analyzed in demography and economics and sociology. For example, when these people entered the labor market at the end of the 60s and 70s, there were more people, more well-educated than previous cohorts, but now they were competing for more jobs. So although they were better educated, there were more of them in the labor market, they were competing for jobs, that had a negative impact on their earnings. So there are several studies that were done here in the US. It started being done more at the end of the 70s and 80s. And now the same cohort is now entering retirement ages, and then they put pressure on the Social Security system, as I mentioned before. And when I mentioned about my PhD dissertation that I did about Brazil, was following the same perspective as the studies done about the baby boom cohort in the US. There in Brazil, people are getting better educated now, they are getting older, they get into the labor market, they start to compete with each other. Better educated people, older people usually have higher earnings than others, but because now they have more people in those groups, there is also a negative impact. So that's where I got my literature review from my specific study. And this is just to give an idea of the overall size of the 7 birth cohorts that between 1900 and 2010. So the New Worlders, they added up to 28.9 million, hard timers 37, and then we reached the lucky few, which were around 41 million. And then you see the jump between the lucky few and the baby boomers. The baby boomers, they were pretty much 80 million people between this time here. And between the time, the overall number of people that were born exactly between these years, 1946 and 1964. So you see a jump from the cohort of the lucky few to the baby boomers. And that's what put pressures as a whole on the society. It's good for the society because you have a more dynamic population and in a few years more people working, but at the same time, you have to provide more services to those people when they're younger, education, and then afterwards jobs, and then afterwards retirement benefits. And here I started a new subsection talking about the Lexis diagram, and here that's where I added some slides. The Lexis diagram is pretty much a graph, a really simple graph using information about time and age of people in a specific population. And it's just really powerful for demographers to understand how the population is growing or declining over time, right? So the Lexis diagram pretty much provides a relationship between the chronological time, T, which is in the horizontal axis, and age, X, which is in the vertical axis. And each person in this Lexis diagram, if I want to draw a line for each person in this Lexis diagram, this person will have a lifeline. And they would start at specific time B, when the person was born, and age 0. That's the age of the person when the person was born. So let me just go to the next slide here. So someone who was born in 19, let's say here, 42, that person starts here. And as we add 1 year, that person gets 1 year older here. And then that person, if we pass 2 years after that, the horizontal axis, the vertical axis, people are 2 years old now. And as these people die, then they disappear from our Lexis diagram. So the lines start in the year that the person was born and finishes in the year that the person was born. Sorry, in the year that the person died. And here is the age that the person died. And of course, everybody when is born is 0 year old. But here, each one of these lifelines, they represent one person in my population. So the line goes up to the right with a slope equals to 1. So people age 1 year in 1 calendar year, as I mentioned. And the lifeline goes up until time and age of the person's death. If you were doing the Lexis diagram for subpopulations within a country, you could also take into account migration. So people getting out of the population could be done both to death or emigration, people getting out of those places. In that case, if you consider migration, people can enter this population older than 0. So if someone moved to this place at the age of 20 in 1940, the lifeline of that person would start from here, 1940, at 20 years old, and then it would go up until that person dies or that person moves out. But usually the Lexis diagram does not take into account migration, it's just taking into account birth. So that's why everybody starts at age 0, and death. And that age can vary from person to person. So the Lexis diagram is a really important graph in demography. I got this from another textbook. This textbook is actually available for free. The ebook is available for free for faculty and students. So you can just check in the university library. And it's a more methodological book. There is another course in this sociology department called Demographic Methods. That's SOCI 320. And then I go in more detail about methods of demography. But 312 now is more substantive, but I'm just giving you the highlights of these methods here. So we can explore a little more the Lexis diagram. If you want to find the population size, we pretty much draw a vertical line upward from the time point and count how many lifelines cross that vertical line. So let's see in this example here. Let's say that each one of these lines is one individual. What's the population of that specific place in 2000? It's pretty much 2 people, right? Because we draw a vertical line here from that year 2000, and it touches these 2 lifelines. That's exactly what's written here. Draw a vertical line upward from the time point and count how many lifelines cross that vertical line. To find how many people survive to a specific age, we do the opposite. We draw a horizontal line across at the height of the corresponding to that age and count how many lifelines cross that horizontal line. So if we go back, how many people between 1990 and we expect to, and based on our projections up to 2200, we expect to reach the age of 60. So we draw a horizontal line here, all across history. History in this case from 19, exactly, Leah, 5 people. 1, 2, 3, 4, 5. Those are the lifelines that touch or cross this horizontal line that comes on the age of 60, right?
Wouldn't it actually only be 4 since the first one starts before 1900?
Wow, that was good. Yeah, let's just say, yeah, that's good that you caught that. So I just rephrase the question. I could say like throughout, like based on all the data that's available in this Lexis diagram, how many people reach the age of 60? But yeah, really good observation. Yeah, this person, he was born before 1900. But so that's good that you understand the logic. That's what I wanted you to do. Thank you very much. That's cool. And like I mentioned before, immigrants start at age and time of immigration, and immigrants that get out of the Lexis diagram for that specific country at the age that they move away. Okay? So how do we see the cohort in the Lexis diagram? We talked about before about cohort and now about the Lexis diagram. So cohort is the group of people sharing the same birthday. In this case, we are talking about birth cohort. These are groups of individuals follow simultaneously through time and age, and their lifelines run diagonally up the Lexis diagram together. In a cohort, time and age go up together. And a birth cohort, they share the same experiences as we mentioned before. So a better way to see it, instead of using the lifelines, it's just better to use the Lexis diagram in a more aggregated way. And then you see a specific birth cohort of people born between, let's say, 1910 and 1915. Those people were born here. They were 0 years of age between that time. And then as time goes by, they start to get older. And so the Lexis diagram shows us information of a specific time point, which is usually referred as the specific time period information. Also tells us people that reach a specific age group, as we saw before in those 2 questions that I asked. But we also can follow people that were born around the same years and see how they go as they grow older. So when I have, for example, a census in 1980 here, and I count all people in that specific year in a specific country, I have a period data. I have data for a specific time period. That specific time period has people from different age groups. So I have a lot of these horizontal bars here crossing my column. And I also have a lot of people from different cohorts. I have different diagonals here crossing my vertical column, right? This, whenever I have like data from a specific year, and I call it, I have period data, sometimes it's also, people use the term, you have cross-sectional data. What is cross-sectional data? It's pretty much data from a specific year about your population, right? It's the same thing as period data and cross-sectional data. Why is it called cross-sectional? If you think as the cohorts as different sections of people getting older together, this period data here crosses a lot of different sections, a lot of different cohorts. It crosses a lot of different cohorts. So period data, it's also referred as cross-sectional data. Yeah, sorry.
Okay, so if, like, by age 40, so by age 40, like half of the population of the cohort has died, does the cohort line get thinner or something, or like
Yeah, so the question here in the classroom, if like by age 40 in a specific population, half of the population die, would the line of this cohort here get thinner? Usually the way that's represented is with numbers. You would just write down the numbers, the width of this diagonal and the width of the column for period and the bar for the age group. They remain the same because they are more, for age is about the age interval, cohort is about the time interval that people were born, the period is the time interval that we collect the data. But if the way that we represent it, we usually write numbers within this here. So you might see the representation of the Lexis diagram, not even with the lifelines. The lifelines is really to see, because if you get a bunch of lifelines together, you know that there are more people. And if they get more sparse, then you're gonna see that people start to die. This one here is just a simplification, just to show you that with the Lexis diagram, we can do analysis of age, period, and cohort. I'm not representing any numbers. If I want to represent the size of the cohort over time, or the changes of people that reach age 40 or whatever age I want to do here, or the size of the population in a specific year for different age groups, then I would write numbers within it. So you might see representations of the Lexis diagram, more word, more concerned with what you just asked, but you would see numbers within this column, bar, or diagonal. Cool? So the period is also called cross-sectional data. The cohort, question? In this group here, in this representation of the Lexis diagram, the person asked me if each line, he asked if like each one of these lines represent one person. In this representation, yes. Each one of these lifelines represent one individual. This is this one here. Each person has a lifeline in this representation here. In this representation here, I'm grouping them. I'm grouping people that were born from these 2 years here, let's say 1910 and 1915, and I'm grouping them and putting them all together. So in this case, I would not represent it with lifelines. I would represent it with numbers going down here over time as people die, right? So period data is cross-sectional data. Let's say that I was able to get information about these people here when they were born. I went there to these households and I interviewed their parents, and then I got a bunch of information about these kids that were born there: birth weight, race, ethnicity, sex, education of parents, income of parents, and everything. And let's say that I have really control of where these people live, and every 10 years or every 5 years, I go back to those same households and interview the parents of those kids. And let's say that those kids leave the household, but I'm able to follow them. And it's a small population, I'm able to follow them over time. And as they get older, I'll be able to ask the same questions to them as they get older, about their education, job, income, and so on. When I follow the same people over time and collect information about them, I have longitudinal data, or is also called panel data, P-A-N-E-L, right? So I have, whenever you hear the term, oh, you are doing analysis using panel data or longitudinal data, that's because you are following the same group over time and asking those similar questions over time to those people. So we have different waves of collecting data. So this term waves is also used when you are doing longitudinal analysis. But most of the time, this kind of longitudinal data is really rare because it's really expensive to find exactly those same people that you had back in some years ago and find them in more recent years. So what we usually do, we get data from a specific period, here 1980, and I say, oh, these people here that are in this area, they were born exactly from this cohort. In 1960, it's gonna be right here. People in this area here are people from this cohort that were born back then in 1910 and 1915. So I can get a lot of like period data and reconstruct a specific cohort. In that case, I'm not interviewing exactly the same people. Usually, for example, when I have census data for 1980, 1960, 1940, I have a sample of people in each one of those years that's representative to the population in that specific year. But maybe the people who are answering the census in 1940, the more detailed questions, they are not the same ones as the ones that answer the census in 1960. But the idea is that those people are representative to the whole population of a specific country. So I can kind of try to reconstruct the cohort. I can say that I will pretty much use data from different periods. I will get all this cross-sectional data and put them together. I will aggregate this cross-sectional data, and then I can reconstruct different cohorts, right? So that's one possibility. Demographers use that a lot because we have more older data going back to the census, but they are not the same people being interviewed in each one of these years, right? So if I interview the same people over time, that's longitudinal data, but I can also do some cohort analysis, putting together information from different periods. But that data is not longitudinal because it's not the same people answering the questionnaire, okay? And of course, if I want to see how a specific age group has been varying over time, the comparison that I do here in the horizontal are not the same people. These are people that were around 35 years of age here, and then I just want to see how their characteristics change over time. How their fertility changed, the fertility declined, education improved, income improved, so I can do that analysis as well. So when we calculate a period measure, the vertical, the column, the vertical representation that we saw in the graph, we pretend that age-specific rates we see today for different age groups continue unchanged into the future. We are actually creating an imaginary cohort whose life experience is pieced together from the experience of different people found at different ages in one period of time. What am I saying here? It's really expensive to get information about a specific cohort over time and follow people over time. So one possibility, the first one that I mentioned before, is get data from a lot of different periods and then reconstruct this cohort, but with people, with different people that were interviewed in each one of these years. So I'm reconstructing the cohort using period data. And then I have another way to do my analysis as well. It's kind of like a little bit the opposite. I have just one period. I'm not getting all these different periods. I'm just getting data from the census in 2000, for example, for a specific country. And I'm saying, based on the mortality and fertility rates from these people here, if a group of people throughout their lives experience these fertility and mortality rates, what would be the overall life expectancy that these people would live based on the mortality rates, and what would be the average number of children that woman would have based on the fertility rates. So see, this is a game of pretend that Wachter mentions in his textbook. In this case here, I'm not doing what I mentioned before. What I mentioned before was different. I'm getting data from different periods, and I'm reconstructing the cohort based on where it intersects with my period, with people, different people being interviewed in different years. In this game of pretend, I'm getting data for a specific year and saying, if people experience those rates of that specific indicator that I'm analyzing, what would be the average of that indicator for those people? So example, based on the 2000 census for a specific country, we get a life expectancy at birth of 75 years of age. What does it mean? Based on the mortality rates of these people here in 2000, if a group of people experience that mortality between, in this case here, it's like only from 0 to 30, but let's just imagine that's from 0 to 100. If those people experience that mortality throughout all their lives, how many years on average they would live? Why is it a game of pretend? Because when I'm 0, and when someone is 0-year-old here, that person is going to have a specific risk of dying. That person, when that person reaches 5 years of age, the actual risk of dying will be measured right here. When that person is 5 years old in 2005. Wait, but I'm not getting information from the diagonal in this example. I'm getting data from here. So I'm getting data from here. I'm getting data about the 10-year-olds from here. I'm not getting it from here. I'm getting data for 15 years old from the column, not from the diagonal. So I'm just saying, based on information from that specific year, people on average, if they were exposed to those mortality rates, they would live 75 years of age. So that's a hypothetical measure, because we are kind of forcing these rates to be constant over time, but they will not be constant, they will change over time because mortality has been declining. If I get fertility rates of women in a specific year in 2000, and I say, and I'm getting information about fertility of women between 15 and 49 years of age, which is the standard age group to estimate the fertility rates, as we're going to see throughout the course. Based on the fertility rates of this woman, how many children on average are they having? Oh, it has been 2.1 children per woman. That's also a game of pretend, because I'm getting information from a specific year and say, if women throughout their reproductive ages between 15 and 49 years of age, how many children they would have on average if they had these fertility rates here. But these fertility rates will change as this woman changed from 15. From when that woman is 15, oh yeah, the information would come from here. But when that woman is 20, actually the information about fertility rate should come from here. But I'm getting from the column, right? So I'm pretty much using information from a specific period to create these hypothetical cohorts. And that's what's called a synthetic cohort. We call this imaginary cohort a synthetic cohort. We piece together all this different information here from this specific period, and we are saying that people would kind of follow this experience over their lifetime. But we know that's just imaginary, it's pretty much a hypothetical work, but it's really useful because then I can compare data from 2000 to 2010, 2020, 2030, and compare if fertility and mortality are changing over time. Age-specific cohorts rates of the synthetic cohort are the age-specific period rates of the period population. So we are getting data from the period and kind of putting it into this hypothetical cohort in the diagonal. So it's coming from one column and going to one diagonal. The concept of synthetic cohort is central to demography because here we have data in one time point, and we kind of can imagine if people were exposed to those rates, how they would be in the future. So here we have one period, and we are constructing one cohort. In that example that I gave before, we would need data from different periods to reconstruct the cohort. And in that case, not longitudinal data again. Any questions? I know that this part here is more technical, but the Lexis diagram is a really central feature in demography, and it allows us to understand a period, cohort, and age variation over time, right? So that's really good to know this, this diagram. And this part here is new also. In the Lexis diagram, most of the slides were already there before. These slides here about ratios, rates, and probabilities are new. I pretty much want you to understand the differences between ratios, rates, and probabilities. And usually people use them incorrectly. If you understand this here and you start hearing people using the terms ratios, rates, probabilities, usually they are not careful and they're not using it correctly. Ratios compare the size of one group to the size of another group. As we're going to see, the sex ratio for a specific population. In the numerator, we divide the number, we get the number of all men in that population. And in the denominator, we put the number of all women in that population. Divided one by the other, I'm comparing the size of men to the size of women in that population. All right, I'm separating the population in two groups and comparing their sizes. Rates is another form of indicator. They describe the number of occurrences of an event for a given number of individuals who had the chance to experience that event per unit of time. In this case, the denominator has a chance to experience the event that's being measured in the numerator. That was not the case of ratios. Ratios, I separated two groups based on the specific characteristics of this population. I separated them in two groups. They are either in group A or group B, and I just compare the size of one by divided by the size of the other. Rates, the denominator, I'm putting there, what's the population that has the chance of experiencing the event that I'm measuring in the numerator. So those graphs that I showed for the coronavirus pandemic, I had the rate of cases of COVID-19 in the US, for example, for each one of those days. Why is it rate? Because the numerator are cases that were observed for that population of COVID-19. The denominator is the population. The population, the denominator, has a chance to experience the event that's being measured in the numerator. In that case, the cases of COVID-19. The death rates, the same thing. They're called rates because the denominator are, we included the population in the denominator, right? Fatality rate, the denominator are people that were diagnosed with COVID-19. Numerator are the ones who died. So the ones who have COVID-19, they have a chance to experience the likelihood of dying for that disease. So that's the fatality rate. Positivity rate. Positivity rate, the denominator have the number of people who got tested by COVID-19. Those people who get tested, they have a chance of getting a positive test on COVID-19. So that's positivity rate. So those are all rates. The denominator can vary. For the case rate, the denominator was population, numerator cases. Death rate, deaths divided by population. Fatality rate, deaths divided by cases. Because people who were diagnosed with that disease have a chance of dying, have a chance of moving to the numerator. And positivity rate are those who get tested. What are the chances of them getting positive, right? So there are different rates there. The denominator can vary, but the idea of the rate is that people who are being counted in the denominator have a chance of experience the event that we are measuring in the numerator. That's the basic explanation about rates. And probabilities divide the number of events by the total number of people at risk in the relevant time frame. The main difference between rates and probability is that rates takes into account in a specific time period that some people could die and then would not be exposed through all that time to experience the event that you are measuring in the numerator. The probabilities does not do it. You just get the overall population at the beginning of the period, puts in the denominator, and then measure the event in the numerator, right? So that's the main difference between the two of them. So I'm going to just go a little bit more in detail about each one of these indicators and give examples. So ratios describe a relationship between two numbers. Compare the size of one group to the size of another group. Compare the relative sizes of categories. Indicate how many times the first number contains the second number. So it's just different ways to explain the same thing. The denominator is not at risk of moving to the numerator. When we say risk here, even put in between quotes, they don't have a chance of moving to the numerator. Risk here is not just linked to mortality. It could be fertility, migration, or whatever. I'm just saying that the denominator is not, people being counted in the denominator do not have a chance to move to the numerator. And usually we multiply by 100 to get percentage information. So sex ratio. We get data from a specific census, and people either classify themselves in a specific year in a specific population as male or female. So I get the total population of males in that specific population, that specific year, and divide by the population of females. This population of females is not at risk of moving to the numerator, right? And because this number here can get a little difficult to understand if it's just one number divided by the other, usually people like to multiply by 100. In a specific year, in a specific country, people can have just a specific age. So I can estimate the total dependency ratio. In a specific country, in a specific year, I can get all people who are between 0 and 14 years of age and put them here. And get all the older people and put them here also in the numerator. And the denominator, I put the people in working ages. Those are the people between 15 and 64 years of age. In this case here, you could say, oh, but next year, someone who is 14 is going to become 15. So that person would move to the denominator. But for a specific year, in a specific country, or in a specific area, people are being classified either as in one group or the other group. That's the idea. That's why they are different groups. And I'm comparing the size of these different groups. The sex ratio gives us an idea of how many more men are, or how. So is it always male, female when finding out sex ratio? Does it matter? Always. That's the standard in demography. Males divide by females. Whenever you use the term sex ratio, number of males divided by number of females. That's the standard, and that's how it has been. If you divided females by males, that's not called sex ratio. And in the past, people used to call sex ratio, I don't know if in the US, but like in Latin countries, masculinity ratio, but it's a really sexist way to refer to this indicator. So we just mentioned sex ratio. And that's a good question because in demography, we have a lot of standards. I mentioned to you just before about fertility. When we calculate total fertility rate, the average number of children that women are having in a specific country in a specific year, we usually get information from women between 15 and 49 years of age. Oh, but there are women having children before the age of 15 and older than the age of 49. But the standard in demography is this, and allows us to compare to other countries and allow us to compare with other years. Oh, but I want to do a specific study here in Texas about teenage pregnancy or teenage fertility rates. Then it would matter for me to analyze also women between 10 and 14 years of age. Yeah, you can do a deeper analysis for that specific country and that specific year. But you would lose comparison with other places. So in order to have more comparison, demographers use these standards. The same thing for the total dependency ratio. Total dependency ratio can see some variations. The denominator, the working age population, could be just people between 15 and 60. Or some people say, oh, some specific countries people work until older ages. So it would be 15 to 69. But this is the usual standard that if you go into the United Nations data, World Bank data, or some other agency, and you want to compare them over time, you have to follow this standard. So this question is good because it's kind of saying, we have these major indicators in demography. They have a way to be estimated. And it's really good for us to know what exactly is the age group that we are analyzing, both in the total dependency ratio in this case and fertility rate, and also who is in the numerator and who is in the denominator. Why the total dependency ratio is good? Because it shows us how much bigger is this dependent population compared to this population that's more produced in a specific country. We know that in some specific countries, there are children working and there are older people working. But the idea is that usually people work between the 15 and 64 years of age, and we want to know how big is the size of those people who are producing compared to the people who are consuming without producing, children in the elderly population, right? And Leah, did I answer your question? So the simple answer is yes, it does matter. Okay, so it should, yeah, thank you. So examples of the sex ratio here. This is data that I got from the United Nations, from their projections that, from their data that back in 2017. And here we have like the world divided. We have the green line here, the more developed regions, the more developed countries all grouped together. The less developed regions in orange, China in red, and the US in blue. So the idea here is to show like why, in this case here, those countries that are, those groups of countries or countries that are below 100, it means that we have more women than men. If the denominator is higher than the numerator, and we multiply it by 100, if this number here is higher, then we're going to have a number that's below 100, which is the case of the US and the more developed regions. In the less developed regions, is the opposite. We have more men than women. For every 100 women, for example, in 1950, in the less developed regions, for every 100 women, we had 104 men. For the more developed regions, for every 100 women, we had only 91.8 men, right? That's how you read the vertical axis here. Why is that these less developed countries, they have more men than women? Usually in those countries, there is a preference for male birth, for boys to be born. So in a lot of those countries, what happens is that if a boy is born and the couple knows through ultrasound, they might perform abortion exactly. If the woman is pregnant of a girl, they might perform abortion because they would prefer to have a boy. And that was really clear the case in China with the after the implementation of the one-child policy, that parents would be able to use government benefits to their children only to the first child. Even with the one-child policy, usually the total fertility rate in China was around 2, but the government was trying to make people have only one child. And because in the Chinese population, they have a preference for boys, there would be a lot of sex-selective abortion when women were pregnant of girls, and then the sex ratios get really high. We have more men. In more developed regions, there is no real preference for having boys or girls. There is not this sex selective abortion being performed. So why are these numbers below 100? Why is it not more closer to 100% here? Why we have less men than women in these more developed regions? Who lives longer, men or women on average? Women. Women live longer on average. So in these countries, if we have similar number of boys and girls being born, over time, since women, they live longer on average than men, you will have overall more women than men. So you have less men than women, right? So really simple graph. I got it from the United Nations, but it gives us already some idea of how sex ratio varied through time within these groups of countries, and actually vary between this group of countries. Through time here, you see that as more developed regions, mortality start to improve not only to women, but also to men, the sex ratio starts to be closer to 100, because now men start to live also longer, and then this the sex ratio starts to increase over time, right? The total dependency ratio, this is data from India, China, and the United States, and it's also in percentage. And for India, you see that the total dependency ratio increased up to the mid-1960s, and then it started to decline. This is mostly caused by declining fertility. So if you go back to the formula, when you have a declining fertility, this population here gets smaller, the population of children. The numerator gets smaller, then the total dependency ratio falls down. But even in India and in other developing countries, mortality starts to improve. When we say that mortality improves, it means that mortality declines. When mortality declines over time, what we expect? We expect that the number of older people will increase. So the overall total dependency ratio will start to increase back again. Maybe it's not going to increase to these high levels that we had in the past, in the green line here for India, but you start to see some expected increases for the next decades, exactly because fertility declined, so you had this overall decline. But as people start to live longer because of improvements in mortality, then you start to see projections expecting an increase in the total dependency ratio. For China, fertility rates declined a lot, and exactly after like all the implementation of the one-child policy, and also not just because of the policy itself, because of improvements in social economic status. People now, it's more expensive to live their lives. They're moving to the urban areas, and then people start to have less children. Having less children, the overall total dependency ratio declines. And now, because of improvements in mortality, people start to live longer in China, and then the overall total dependency ratio increases. And this is a really steep increase. So the decline is caused by this group of children getting smaller because of fertility decline. And it goes up again because of mortality improvements. You start to have more elderly population than before, right? And in the US, you also had some declining fertility. in the late 70s, 80s, 90s, and 2000s. And then again, the same reason. People start to get older, total dependency ratio starts to increase. But of course, people can get older, but there is a limit in our chances to live longer. And then the total dependency ratio overall in the US starts to get more stable based on the projections for these coming years, right? What we're gonna see in the next lecture, based on chapter 10, is that we can have also, we can break down this total dependency ratio. In the numerator, we can put just the children, so it'll be the young dependency ratio, or only the elderly population, so it'll be the old age dependency ratio. You have a question? No? You just moved your hand, I thought you had a question. Yeah, so those are examples of ratios. The examples of rates. And this is, I got it from this other article, and I put the reference at the end of this lecture here. Rates are instantaneous measures that range from 0 to infinity. Rates describe the number of occurrences of an event for a given number of individuals per unit of time. Rates consider the time spent at risk, at the chance to experience the event that we are measuring in the numerator. So for example, numerators are number of events. Examples of this number of events: number of births, number of deaths, and number of migration that we see in a specific population. Deaths we can do by cause of death, such as the examples that I gave about the coronavirus pandemic. Migration, we can have immigration rates or emigration rates. The immigration rates, we count how many people entered a specific country in the numerator. Immigration, we would put the people who left a specific country in a specific time period in the numerator. The denominator includes time. That's the difference between rate and probability. And in this case here, the denominator sum is the sum of each individual's time at risk of experiencing an event for a specific population during a certain time period. This explanation here, this concept here, is known by demographers as person years. What does it mean? Let's say that I want to estimate the death rate of a specific population in a specific year. I say the crude death rate. I just put the population, the overall population in the denominator, and the number of in the specific year, and then in the numerator I put the number of people who died in that specific year in that specific population. The correct way to get information for the denominator of that formula is to know how much time specifically each one of the individuals in that population was at risk of experiencing the event that we are measuring in the numerator. So if I'm alive in January and I die at the end of June, so I was exposed to the risk of I died, but I was exposed to the risk of dying only half time of that year. So I should not count as 1 in the denominator. I should count as 0.5. People who are alive in January 1st and are alive in December 31st, they were alive throughout the whole period. So throughout this whole period, they had a chance of dying, but they did not. So they count for the whole year, 1 year. They count as 1 in the denominator. And so on. If someone dies in the end of September, that person should be counted as 9/12 in the denominator, right? So but that starts to be really difficult, right? Because we would have to get the population pretty much per month of that country. And it's already hard to find population for several countries in a specific year. Per month within a specific year would be really hard. So a way to approximate some strategies that we can use approximations for the denominator is that instead of using this person years, exactly the fraction of time that you were exposed to the risk of experiencing the numerator, we can simply use the population in the middle of the period. So a simple way to do it is just to get the population in July 1st, and use that population July 1st as the denominator of your formula, of your rate. Or if you get the population in January 1st and the population in December 31st, you can just take the average of them and use that average of the starting and ending populations as the denominator of your formula. What's the assumption that we have when we use these approximations? That people are dying pretty much in the same probability or the same chances throughout this time interval. If I get the population in the middle of the period, this possibility here, or I get the average of the starting and ending population, I'm saying, well, people are dying pretty much with the same chances throughout this year between January and December. There's not much variation of people dying more in April than in September, than in October, and so on. So we can just get these specific time points, middle of the period, or the average of the starting and ending populations. So technically, the correct way to estimate the rate is to use person years. Know exactly how much time that person was exposed within that specific period that you're analyzing. In the period here, I'm talking about 1 year, but I could be talking about a rate that estimates the mortality rate between 2000 and 2010. In this case, I'm just talking about 1 year. Within that 1 year, the person might not have been exposed to the risk of dying the whole time, except because the person might have died before. But it's really hard to get data about person years. So we use these approximations. In this example here, I'm just showing you the crude birth rates and the crude death rates. It expresses the number of actual occurrences of an event versus the number of possible occurrences per some unit of time. In this case here, I'm just concentrating on births and deaths. And I'm getting the number of births in the numerator divided by the total population. The total population here is the population in the middle of the period. We are getting an approximation. We are not actually using person years, the data that I'm going to show you here. The crude death rate, the same idea. Number of deaths that happen in a specific country in a specific year, divided by the total population in the middle of the period. Since these rates get really small numbers, we multiply them by 1,000 in this case. There are some standards, like the sex ratio is by 100, the total dependency ratio is 100, as you saw before. The crude birth rate and the crude death rates are by 1,000. Homicide rates are usually by 100,000. Whenever this number starts to get really small, we multiply by a bigger constant. Sorry? The question in the classroom is like, why for the crude birth rate include that death rate we are using 1,000, and back for the sex ratio and the total dependency ratio was 100. It's just a convention, again, demographic convention, because total fertility, total dependency ratio and the sex ratio, it's hard to understand one if you divide one by the other. But if you multiply by 100, it makes sense. We're going to say that, oh, in this country, we have 104 men for every 100 women. But when we get the overall number of births in the population and we divide by the total population, this number gets really, really small. And then even if we multiply by 100, this number would be small and difficult to understand, to interpret, because there are so many decimal cases. So that's why it was multiplied by 1,000. That's a convention. And you're going to see this convention for different indicators. Like for the indicator about homicide rates, the convention is multiplied by 100,000. Because the number of total homicides divided by the total population gets so small. And remember, the total population in the US is more than 300 million people. So this number can get really small when it's about births, and for homicides can be really small as well. So for example here, see the vertical axis. We had like the data for crude birth rate in the US for data from 1950 to 1955. We had 24. This number is easier to interpret. For every 1,000 people in that population, 24 people were born in that specific year in the US. If we had multiplied by 100, this number would be 2.4 people being born for every 100. It's still possible to understand it, but for crude birth rates and crude death rates, that's the standard that we use. And exactly because births have been declining over time, we see this decline in the US in the 60s and 70s, and then keep declining, but then we start to see some projections that say it might decline still over time, but it's much more stable than it was in the past.
So, in essence, we'll multiply on whatever number we need for a per capita ratio just to keep the fraction manageable.
Yeah.
It could be like times 100, times 1,000, or times 10,000, just to the point where the numbers are manageable, correct?
Yeah, the question is also about like the constant here. When do we decide by 100, 1,000, 10,000, 100,000? Usually you check for that specific indicator that you are analyzing, what's the convention? We usually don't create whatever we want. So although I mentioned here before, I could have, if I had multiplied only by 100, this number would be 2.4. It's still easy to interpret, but that's not the convention. And usually the convention of crude birth rate and crude death rates is per 1,000. The convention for homicide rates is per 100,000. So I would check for that specific indicator that you are analyzing and you are estimating, what's the convention, right? And that you check pretty much by look at other articles that are dealing with that same topic that you're doing, or look at the United Nations or World Bank, the Census Bureau. They all have examples of these indicators, and they are implemented exactly the convention that's more used for that specific indicator. Cool? The crude death rates, they have been more stable over time, declined a little bit in the 80s and 90s, and then it started to increase a little bit. Why does it increase a little bit and more? We expect to increase a little bit in these next decades. Because the population gets older, and the crude death rate, see, we are not actually taking into account the subgroups of ages, as we're gonna see in the mortality rates that are for age-specific groups, the age-specific mortality rates. Here, we are just getting the overall number of people dying divided by the overall population. As the population gets older, more people will tend to die. So that's why you expect to see this increase in these next decades. But that doesn't mean that the health system and the mortality is getting worse in the country. It's more because the population is getting older. But with the pandemic now, it might create, it will create pretty much a discrepancy here based compared to previous expectations that we had for the future. The pandemic creates what social scientists call a natural experiment. It's something that nobody was expecting, this pandemic, and then it might change the pattern of these rates in these next decades here. And that can happen for anything. Unemployment rate, death rate, birth rate, migration rate, and so on. Natural experiments, for example, a hurricane, an earthquake, all those are natural experiments, and the pandemic is the same thing. And you might have seen, for example, the unemployment rates in the US, that they increased a lot, and exactly after the pandemic now. So that creates the natural experiment that demographers will start, or economists, social scientists in general will start to investigate in these next years. Probabilities, they describe the likelihood that an event will happen for a single individual in a given time period and range from 0 to 1. It does not include time in the denominator, and it divides the number of events by the total number of people at risk at that in the relevant time frame. Just to better understand the difference between probability and rates. For rates, we are taking into account time in the denominator. because people can live the whole period or they can die within that period. So they are not exposed to the risk of going to the numerator throughout their whole time necessarily. For probabilities, what matters to me is the population at the beginning of the period. So an approximation for the denominator of probabilities is getting the population at the beginning of the period. So the denominator of probabilities would be the population, for example, in January. And remember, what was the approximation for rates? The population in the middle of the period, July, or the average between January and December, right? Because here we're interested on the risk of that, those people are, how likely they are to experience this event based on the population that was in that specific country, in that specific year, at the beginning of the period. So this is the article that I included there that goes more in detail about rates and probabilities. This is a textbook that I use a lot in my advanced methods class, the SOCI 420 here at A&M. This is the main textbook, the chapter 1. This is another textbook in population that's also important, and I usually get information from them. This book here is the one that I use for that example of the database of workers. So these are the references. The quiz 1 is open now. I suggest you, before you start it, review a little bit the slides. If you want to wait to watch the lecture again on YouTube, you can wait it. Have your notes with you. Have the slides open with you later when you will take the quiz. So you do a great job. And read those instructions that as I mentioned, okay? So thank you very much and have a great weekend. I see you guys on Tuesday. Thank you.